So independent events are so important that I feel like we need to have a whole section just devoted to them. So here are some things about independent events. If A and B are independent, then the probability of A given B is the same as the probability of A, right? That's kind of what we used to mean that things are independent, right? Here's another property that just kind of follows from that. And it's sometimes used to define what it means to be independent. That is that the probability of A intersect B is the same as the probability of A times the probability of B, right? And realize that that is true. If the probability of A intersect B is just the probability of A times the probability of B, okay, then the probability of A given B, which is the probability of A intersect B divided by the probability of of B, that's just probability of A times probability of B divided by probability of B, and these will cancel and you just get probability of A, right? So that's why those two are kind of equivalent definitions, okay? Now, the probability of A given B is just probability of A. Like I said, those are equivalent. How about the probability of B given A? I mean, I said that they're independent, right? So probability of B given A should kind of be the same. And actually, it holds because the probability of B given A is the probability of A, or I should say B intersect A, divided by probability of A. But we know what that is. That is the probability of B times the probability of A divided by the probability of A. And again, those cancel and we have probability of B, right? So if the probability of A given B is probability of A, then the probability of B given A is probability of B, right? Independent is really the right word, right? Because, it implies that it goes in both directions, right? Knowing something about one does not tell me anything about the other. Okay. Now these are, I must say, somewhat unintuitive. So, for example, let's talk about the lottery. Okay, and the Powerball lottery has the following rules. You have 5 white balls, right? And they come out of a drum that has 69 balls, right? And we take them out without replacement. We don't take out a number and then put it back in. Okay. But in any order, right? We don't care if you get the 3 and then the 7 or the 7 and then the 3. Okay. Now, the other thing you have to do to win a Powerball is you have to match the red ball, and the red ball comes out of a different drum that has 26 balls. Okay, so what's the probability of winning? Well, the probability of winning is, you have 5 numbers, right? We don't care about the ordering, okay? And those have to match the numbers that come out of the drum, okay? So I'm being somewhat pedantic here because I'm emphasizing the fact that about the ordering. So what I'm doing is I'm saying, oh, then what I have, I have 5 slots, and this one I can fill in 5 ways because that's how many numbers I have, and then 4, and then 3, and then 2, and then 1, and then I don't care about ordering, so I divide by 5 factorial, right? That is, of course, just equal to 1, right? Because there's one way for my 5 numbers to come out. Okay. Now, what am I taking that out of? And the reason that I did it that way is because it makes it easier to explain this one. I get 69 ways of doing the first one, 68 of the second one, 67, 66, 65. This is my no repetition, right? Okay. And then I'm going to divide that by the ordering, which is 5 factorial. Okay. So what I end up with is this number right here is 1 out of 11 million. Not great odds. Okay. And to actually win the Powerball, you actually have to get the red ball. The probability of that is easy. It's just 1 out of 26 because there's 1 ball out of 26. That's the winner. So we multiply these two, okay? And we end up with this number, which is 1 out of about 290 million, okay? That's 3.4 times 10 to the minus 7%. Not great odds, okay? Not great odds whatsoever, all right? Did you notice where we used independence? Okay, I multiplied these two, right? The white balls and then the red ball, and I actually did those using independence. Okay, I did not use independence when I was computing the probability of the white balls. I simply used the same techniques we used earlier of counting, right? But here, that is a pure independence play. Okay, and incidentally, even the counting is a little bit of independence because I'm using the product rule, right? Okay, so it's a property that's extremely useful. Okay, now I want to use independence oh, by the way, before I move on, this is just an aside, but I told you the probability, okay, of winning Now, what is the expected value? And let's say that the expected value is about 500 million jackpot. Okay, so people buy, nobody wins. They buy again, nobody wins, and it keeps going. The jackpot grows, and eventually it reaches stratospheric numbers, and it makes front page news. Oh, the Powerball is up to 500 million. So okay, so what is the fair value of a single ticket? It ends up being about $1.70 because I'm taking the probability of winning 500 million times the probability of winning times the price, the event payoff. That's 170. Unfortunately, each ticket costs about $2, so it's still not a fair play, right? You expect that. When you gamble, you never want the expected value, right? You're looking for the high variance in the returns. By the way, it's even worse than that because when the jackpot gets that high, then lots of people buy the lottery. And so the chances that the person who wins is alone, they're not as good as they are normally, right? So that you could end up with multiple winners, and so each one of them splits part of that price. So the fair value is even lower. And when they tell you that the lottery is 500 million, what they don't tell you is that there's 500 million paid out over, say, 30 years. So it's actually not worth that much. It's worth maybe 300 million. And then they'll take taxes on that, so it's down to 200 million. So really the fair price is quite a bit smaller than that. But still, that's the mathematics are not in your favor. But who knows? Maybe fortune is, and you can give it a shot. Okay. All right. Let's go back to Powerball. We know the rules, right? And we used independence to compute the probability of winning. But suppose that you won the jackpot last Saturday. Okay. And you're, of course, very happy, and you still took time out to come to this class because you value knowledge. So you're very happy, and you're learning a lot. Okay. Now you decided, okay, to actually play in the lottery again next Saturday, right? So what's the probability that you win next Saturday? I mean, you won last Saturday, right? What's the probability that you win next Saturday again? And in fact, let's say that you won the 16 previous Saturdays, okay? And you still buy a ticket for next Saturday's drawing. What's the chance that you win in next Saturday's drawing? And the answer is that, it's exactly the same in any given Saturday because these are independent events. It doesn't matter that you won it last week. It doesn't matter that you won it the last 16 weeks, okay? Your chances of winning are just as good this time as they are no matter what's happened in history. Maybe you've always lost in the lottery. This could be your chance. Maybe you've always won. This could be your chance. Okay, so that's one of the things that's great about probability. Okay, now I'm going to end this section by just sharing with you kind of a little tidbit that I personally enjoy, and that has to do with Michael Jordan, who's one of the greatest basketball players of all time, and he firmly believed that he would get hot, right? And he would get into a streak and would get just a whole bunch of points in a row, and he would take over a game. And somebody actually ran the statistics and tried to figure out, okay, suppose that each shot is an independent event, okay? And you look at his history, you look at how many shots he tried and how many he actually made. That gives you the probability that any one shot results in a basket. So what is the probability now that you have, say, 10 baskets in a row or 20 baskets in a row? And it turns out that if you simply assume independence of events, then you can explain those streaks where he feels like he's getting hot. So maybe he really never did, quote, get hot. It was just fortune is in your favor, okay? That's the way probability works, okay? Now, why he happened to usually get hot precisely when his team needed him to, I don't know. Maybe there is something to those events not being independent.